Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is CSA A23.3 2019 Concrete Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I want to give a brief overview of RFEM, which is our main finite element analysis program, and the add-on module concept for concrete structure design. Then we'll move into our example. I'll give you a brief overview of the modeling and loading within RFEM. And then we'll be able to run an analysis and to view the results. Then we'll move into our first add-on module, RF Concrete Members. So this will allow us to do member design, including columns or beams, according to the CSA A23.3, and we have recently added the 2019 standard. We'll move into our second add-on module, which is RF Concrete Surfaces. So this allows us to do surface design, including slabs and walls, also according to the CSA. Within RF Concrete Surfaces, we will consider deflection checks, and this is using the add-on module extension RF Concrete Deflect. And finally, I'll show you how you can address singularities which may occur in any finite element analysis program. So RFEM is the main finite element analysis program. This allows you to fully model the structure. You can load it. All of our cross sections are available there from the various standards. And we can run a full analysis to get information such as the support reactions, deformations, internal forces. But these add-on modules are used for the design. Now, in particular, today we'll be talking about the RF Concrete add-on modules, which consists of two main modules. The first being RF Concrete Surfaces. This provides an ultimate and serviceability limit state design for any 2D surface. This includes walls or slabs according to the CSA A23.3. We also have the ACI 318, of course, and then many other international standards. The second is RF Concrete Members. Same concept. We can provide the ultimate and the serviceability limit state design for members, so beams or columns. We also can do a deflection check within this add-on module, again, per the CSA standard, but many other international standards available to us. We have RF Concrete Deflect. So this is an add-on module extension within RF Concrete Surfaces. This allows us to run an analytical deflection analysis, either in the cracked or uncracked state, and we also can consider long-term deflection according to the CSA standard. So we'll get a glimpse of that in the example today. The final add-on module extension is RF Concrete Nonlinear. So this we will not be covering today, but this allows us to do a nonlinear calculation for the serviceability limit state only. So this takes into consideration the true crack state of either our section or our surface. We'll determine, rather than with analytical methods of applying what the cracked cross-section factor should be, we'll actually figure out which portions of the section are cracked. We'll reuse the modified section cross-sectional properties for the analysis. So again, not getting into that today, but that is an option for either of these two concrete add-on modules. So we'll move on to our example within RFEM, and you can see I've taken the liberty here to model the structure for the sake of time. There are a few things I'd like to go over before we run our analysis. And the first, we can access the general data dialog box by right-clicking on the model name. Now this dialog box would also be given when you first start a new model. The orientation of the global z-axis is set by default to upward. It doesn't matter, we could either use upward or downward here. But with concrete design, what does matter is setting the local axes under these detail settings to downward. So if you're doing any type of concrete design and using those add-on modules, you want to make sure that this is set to downward. The reason why is because the program will give us reinforcement for the top, but it's actually showing it on the bottom. So the concrete modules were developed to consider this downward. We will be generating our load combinations automatically according to the NBC standard here within our dropdown. We have this checked here, so the program will automatically create those load combinations. We can always uncheck them if we'd prefer to manually create those. I'll be working with imperial units today, but under options, units, and decimal places, you always have the ability to toggle to metric as well. So looking at our structure for the example today, we have some cross sections defined for our columns, and if I double click on this, you'll see that it's just a typical rectangular section, 14 by 14 inches. We have concrete F'(C) of 30 MPa defined for primarily the entire model. We also have what's called rib elements. So you'll notice I have these rib elements defined around the openings, 4 of them. The member type is set to rib. These are a little special because if we go into these expanded settings here, this allows us to define an effective width on both the left and the right hand side of the surface. And this effective width can be considered with the internal forces that we'll use for the reinforcement design. Now we also can drop this rib on the underside of the surface with an automated eccentricity here. So essentially we're going to design this as a T-beam. Looking at our surfaces, if I go to my display here, I can scroll all the way to the bottom and I can view the model according to the surface thickness. So you'll notice I have these blue surfaces, which are my walls, and these are all defined with 8-inch thick surfaces. If I double click here, we can see concrete 30 MPa, 8 inches thick, just a standard stiffness. My slab elements, denoted by this brown color, are going to be 10 inches thick. Now, we also can view the member type by color as well. So this is where we'll see these typical beam type elements, which can be columns as well. And then we have the pink sections here, which are our ribs. Before moving on to the loading, I also want to point out the crack section properties according to the CSA standard table 1014.1.2. So this requires that we apply a factor to the gross moment of inertia for all of these elements. Now this is not something that the program will do by default when we draw each one of these elements. But rather we can select these elements after we've drawn them or in the process of when we're drawing them. And for example, let's take a look at our slabs here. I've already done this, but under the Modify Stiffness tab, this is where we would use the drop-down box here to select the CSA standard. The component type is flat plates and flat slabs, and then we have that multiplication factor from table 1014.1.2 of 0.25, which will be applied to the bending stiffness. Same concept for our walls here, but the only difference is we need to choose the different component type here of either walls uncracked or walls cracked. And finally, we also have our members. I've applied this to both the columns and the rib elements. Again, selecting the CSA standard, we can choose columns here from our drop down, and the ribs will utilize the beams for the correct factor to be applied to the gross moment area, or the gross moment of inertia. So moving on to the loading, you'll see that I have a few load cases defined here, and I can display those. These are just simple surface loads. So dead load is shown here at 0.03 kips per square foot. Across the flat slabs here, we also have what's called a free load. So what's unique about free loads is that we don't necessarily have to apply them to the entire surface, but if I double click here, I can choose the load position. And you'll notice I have 2 coordinates selected here just to apply this free load to the center of the surface rather than the entire surface itself. In addition to the dead load, we have the live load, same concept at 0.06 kips per square foot. We have snow load applied to our roof levels. And finally, we have a simple lateral load here of wind at 0.15 kips per foot. If I go into my load cases and combinations, you'll see that I have my 4 load cases defined here that we just saw graphically with the action category defined, which is related to the NBC standard. Under the combination expressions, we will generate the strength load combinations and the serviceability load combinations. We can click this little info button here to see what those load combinations are directly from the NBC. Under the Load Combinations tab, this is going to list all of our strength load combinations and our serviceability load combinations based on the load cases that we've defined within that first tab. Now notice under the calculation parameters that all of my load combinations are run according to a second order analysis. So this is by default. We will consider a big P delta and little p delta analysis. Under the result combination, this is an envelope solution. So we'll take all of those strength load combinations and we'll run them together and provide you the max and min output. So basically, as I mentioned, result combination is nothing more than an envelope solution. Now we also have this for the serviceability, for our serviceability load combinations listed here. So once we have defined all of these load combinations, we can view them in our drop-down box to see how the loads are being applied to the structure, and they're just compiled on top of each other. So we're finally ready to run our analysis, and we can go to calculate all to calculate all load cases and combinations as well as result combinations. And for the sake of time, I have already done this. So what you'll see here when we run our first analysis is the global deformation. So I'm currently looking at load combination 5 here, and I can scroll through to my different load cases or combinations. We can turn this to a wireframe view. I can decrease my deformation factor here to something quite a bit smaller. I think deformations are important because this is going to initially tell us if we've applied our loads correctly, if we don't have any modeling errors, just to get a sense of how the behavior of the structure is reacting under these load types. So everything looks fairly decent here for the global deformations. Now, we're probably very interested in the internal forces for our concrete design. So we can begin by looking at our members here. And I will highlight just a particular column line. We'll create a visibility by the selected objects, so this is a little bit more clear. I'll turn on my axial forces, and now you can see a nice diagram here of these columns at both the first floor and the second floor. Now this is given as a 2-color diagram, but under the Display tab, this controls everything that we're viewing graphically. So you'll see this entire results section here indicated by these rainbow colors. Under the members, if I want to change from a 2-color diagram, I can change to a color diagram. And we take a look at our control or our color panel over here on the right, and we can relate those colors to those values. We also can choose without a diagram, so we're essentially looking at a wireframe view here with the colors, or a colored cross section. So many different options in how we're viewing graphically our results. So going back to the 2-colored diagram, in addition to axial forces, we can view the shear forces in both the strong and the weak axis direction, torsional moment, and bending. So with any one of these values that we're seeing here graphically, we can right-click on a member or multiple members that we have selected and view what's called a results diagram. So this results diagram will populate here, and what this will allow me to do is to turn on and off these either internal forces. You can see we even have the strains available here. I can scroll through to different load combinations if I like, and it's showing me these values along the member length. We have the ability to export these to our printout report. We can smooth over a particular average region. So this is quite powerful in terms of giving us a little bit more detailed information rather than just graphically viewing them here. Now we also have the results available to us in table format. So I can go here to table 4, which is going to show me all of my results. And down at the bottom we have all of our list here of the available tables, and one of those would include the member internal forces. So you'll see that when I'm within this table, the program is going to highlight in the background exactly which member I'm looking at. That red arrow will show me exactly which internal force, where that location is. We can filter this information here, turning on and off some of the extreme values and where we're exactly displaying them. We can export these internal forces directly to Microsoft Excel. So this would consider the current table and the current load combination, just give you a quick export. This might be important for doing a hand calculation or manual design for the reinforcement. Now in turn, under File, Export, we also have the ability here to export as a Microsoft Excel XLS file. When I click OK, this is the same concept as what I just showed you, but rather under Results, we can choose only selected tables. And this will allow me to select multiple load combinations at once, for example, as well as multiple result tables at once. I can export that to Microsoft Excel, which is just a little bit more efficient rather than individually exporting out each one of these tables, of course. Okay, so that gives a quick summary of the member results. Now we're also interested in the internal forces here of our surfaces. So we can expand these surfaces values here. I'll cancel my visibility mode. And let's just select a single surface, floor number 1 here. So I'm going to highlight all of my nodes and everything at that location, create a visibility by the selected objects, and I'm also going to right click here to turn on the local axis system so we can see X, Y, and Z. So I can view the local deformations of this surface, and we're also are able to view the basic internal forces. So we have bending mx along the x-axis. My would be bending along the y-axis. We have shear values. We also have axial forces. Again, everything given to us graphically here with these contours. Principal internal forces are also shown. So the basic forces that we're currently looking at, these are internal forces based on freely defined x, y, and z axes that were shown here. The difference is with the principal internal forces, we're going to take the extreme values of the surface. So M1, for example, would represent the maximum bending moment in the principal axis 1. We have M2 here, which would be the minimum value along axis 2. We also can view the strains. Of course, graphically, you can see that this is quite a long list of all the different strain values that we have. Now, similar to the members, we of course can view all of this information by table. So if I take a look at my surfaces for my basic internal forces, I have my results listed to me according to the grid points, and this is not based on the FE mesh element. So what I mean by grid points is if we double click on this surface here, we have the grid tab. By default, this will be set at every 1 foot. So our results will be reflected based on this grid spacing. This will give us just a nice representation of our surface results rather than every FE mesh, which isn't necessarily so clean at every 1 foot. The FE mesh can really vary significantly across the surface. Again, we can export this information to Microsoft Excel. We also have the ability with surfaces to make what's called a section cut right through one of these slabs. To do this, I can turn on my grid and I will snap my grid point origin right here to this first column line. To insert in a new section, we can go up to our tools up here in our toolbar at the top and choose Create Section Numerically. I'm going to give it a section name of 1. Then I need to graphically define the edge points of the section. For this, I can just simply snap to my drawing grid point from one point to another right through that column line. And notice it doesn't matter if my points are outside the slab. I'm going to choose my result diagram to be visible in the global Z direction, the positive orientation, and I want to consider only surface number 1 here. So I graphically select surface number 1. So when I click OK, we now have this section cut right through our surface. Now to make this a little bit more visible, what I'll do here is to turn on bending moment in the Y direction. And I'm actually going to turn off my ISO bands up here in my toolbar. So I'm currently looking at the bending moment right through that first column line here. We can take a look at shear in the Y direction as well. And as we'd expect, we have some high forces right here where we have this column framing in to the 2D surface. And this will lead us to a conversation a little bit later on about singularities. But so these section cuts are nice. I'm just making that cut right through the surface and show you the same results that we're viewing for our surface, but only at this particular location. We can also right-click on the section to view the results diagram. This is identical to what we just saw with our members. This will populate all of the information, though, that's available for surface results, and we can turn this on to view the internal forces along the length of that cut. I can also turn on my grid again, and I can snap this point here to my second column line. We can hold down our control key, and we've selected this section cut. I can then just drag and drop here to my second column line. So this is just an easy way to make multiple section cuts at once with that drag and drop feature, and the program will automatically update to the new location. Okay, so turning off my local axis system here, let's take a look at the rendered view, and I'm going to turn back on my ISO bands. This was essentially an overview of the results available to us within RFEM, and this is purely the analysis only. So again, this is the information that we could take into our own design tools, in-house programs, or spreadsheets to do the reinforcement design. But rather today, we would like to take a look at the concrete add-on modules to be used for design directly available within RFEM. Back under the Project Navigator, we have all of our add-on modules listed here, and you can see this rather long list. We also have the add-on modules available to us here at the top under this drop-down, and we can choose the design of concrete and utilize RF concrete members. So the add-on module will be populated here, and you'll see that this is nothing more than just a dialog box within the main program RFEM. We do not need to remodel any of our structure. We don't need to redefine loads or load cases. We're simply going to define information that is specific to our reinforcement design according to the standard within these settings. So the first thing to do is to select here from my drop down the CSA standard, the 2019 version. Then under the ultimate limit state, I'm going to move all of my strength load combinations to the right hand side. Serviceability limit state will be the same concept. I'm going to take my serviceability load combinations and move them over to the right hand side. Now it's really just as easy as moving down this list from top to bottom. My materials are defined here. They're brought in from RFEM as 30 MPa. My reinforcing steel material is selected here within this drop-down box. We will use 500R, and then all of the material properties are shown to me here within this dialog box. The cross sections, again, my 14 by 14 column is brought in, as well as my rectangular rib element, which is 14 by 24. We do have the ability to optimize cross sections as well. So I can check this checkbox, and this dialog pops up that allows me to define different ranges for both my width and my height of my cross section, so that the program can kind of optimize within those ranges. So we won't be optimizing today, but that is an option if you wanted to activate that here. Here is the ribs table, and just like what we previously saw, we have defined an effective width back in RFEM for those rib elements. All the program's doing here is bringing in that effective width information, so we can see all 4 of our ribs listed with the effective width on either side to create our T-beam. The supports tab, well, this will affect our design of our member for moment and shear reduction to account for a column face, for example. So what I'd like to do here is I can select the nodes that I'd like to consider for this support, and let's focus in on this first floor here. So I'm going to select the nodes where the rib is framing into the column. We have 4 different nodes here. I graphically select them, I click OK. And I actually forgot one, so let me go back and do that again. We have 8, 12, and then we'll select 13 and 9. So those are all 4 listed here. This is where, again, that rib is framing into the face of that column. We do need to define the support width. In this case, this would be the width of our column at 14 inches. So I type in 14 into this cell. I click my down arrow on my keyboard, and just a nice little trick within the program, you don't need to retype 14. I can hit F8 on my keyboard, which will copy the cell above it. So now we have support widths of 14 inches for all 4 of these support locations. Is this a direct support or not? So if the beam is introducing load to another beam, this would be an indirect support, and we'd want to uncheck this. However, we have the beam framing directly into the column, which is a direct support. This will affect our development length and our shear force used for the design. We have a monolithic connection. You'll notice here that the picture updates depending on if I have a monolithic or not type of connection. This is really just going to control if the connection is pinned or fixed. So we have that moment release. Now we have the end support. Again, it's pretty self-explanatory with this picture here. Is the beam continuous across the top of that support, or does it end there? In our case, we have an end support. A few more options down here on the lower right-hand side. For example, we can consider the limited moment redistribution of the supporting moments according to 924. What the CSA code tells us is that for this section, negative moments at supports of continuous members can be increased or decreased for an elastic analysis. So when we activate this checkbox, we now have the ability to increase or decrease that moment. The second option here is the reduction of shear forces in the support area according to section 11.3.2. This will allow us to reduce the shear force that we're using for design at a distance d away from the support face, and you can see that's automatically checked on by default. Now we have our reinforcement table here. So this is going to be a majority of the work within these add-on modules. The first reinforcement group I would like to define is for my columns. So we can give it a name up here. I do not want to design all of my members, which would include my ribs, but rather what we can do here is to graphically select all of my first floor columns, and I can just do that with my selection box. I click OK. So now members 1 through 11 are selected here. The longitudinal reinforcement, this is the checkboxes that are turned on or off so that the program can essentially optimize which diameter should be used for longitudinal design. So maybe we turn on the 20M and 25M options. We would want to give it a minimum spacing here, maybe 0.075 inches between the reinforcement. The anchorage type is selected here. We can either choose no anchorage, straight, hook, or bend. You'll notice this picture updates with whichever selection we currently have chosen. Curtailment type. This just means that the program will optimize the longitudinal reinforcement for the member. So this might be a good example for a beam element where we have higher bending moment at the midspan versus lower bending near the support. So the program can optimize with different curtailment zones, for example, to just get a little bit more of an economical design there. The provided basic reinforcement, if we know that we would like to use a minimum here reinforcement for both the top and the bottom, we can turn this on. When these are turned off, then the program will just automatically design the provided reinforcement based on the required reinforcement needed from the analysis. The stirrups tab, again, we want to choose the possible diameters. We'll leave this as 10M. The anchorage type, again, we'll update here according to whichever option that we choose. Stirrup layout, the default here is uniform spacing throughout. Similar to our curtailment options, we can choose different zone-related spacing. So where we don't need as much shear reinforcement, maybe we can increase the spacing there. You can even define your own spacing as well. Now the spacing limit, the maximum stirrup spacing is checked on here according to the standard. This refers to section 11381 where we'll use 0.7D times the diameter of the rebar or 600 millimeters as the maximum stirrup spacing. You also can define a user-defined max and min here as well. The reinforcement layout, so this includes the concrete cover, and to be clear, this is the clear cover. This would be the distance from the face of the member to the edge of the rebar. For our example today, for our columns, we'll set all of this as 1 inch. The reinforcement layout, we can see within this drop-down box, this tells the program how to distribute the reinforcement at both the top and the bottom. So we can have optimized distribution, we can have symmetrical, maybe we want to define a ratio of top versus bottom. For our columns, we want to choose the option uniformly surrounding. So of course we might have biaxial bending here for these columns, so we want to apply the longitudinal reinforcement to all sides, which this picture over here on the right will update accordingly. We are going to design the member for all of the internal forces shown here, which includes axial, shear, torsion, and moment. You can always uncheck one of these if you're not wanting to consider it within the reinforcement design. The minimum reinforcement tab, here we can manually define a minimum steel area. But we also have these two check boxes here which just relate to the standard. For example, the minimum longitudinal reinforcement, this is going to refer to section 10511 where the factored moment resistance must be greater than 1.2 times the cracking moment. The minimum shear reinforcement according to the standard refers to section 11282. As far as secondary reinforcement, this would just be if you would like to apply additional reinforcement not structurally required. So we might see this in the case of designing an I-concrete beam, for example, where we want to add an additional reinforcement that the program isn't putting in there due to the analysis. The CSA A23.3 tab, so this is specific to the CSA standard. For example, the percentage of reinforcement, you can see the default here is set at 8% steel, comparing that to our cross-sectional area of our concrete member. The diameter of the aggregate we would enter in here. Exterior exposure for either the top or the bottom. We don't have this in this case, so we'll go ahead and turn that off. This just relates to section 1062, which inevitably will affect the reinforcement design. The shear and torsion reinforcement section. So this is for beta and theta. These are variables for shear strength according to 1136. The general method is selected by default here according to 11364, but you can always turn this to special member types according to 11362. The strength reduction factors according to 8.4. This comes directly from the standard, but of course you can modify those if you would like. And finally, we have our serviceability tab. So we will design the serviceability, which if we go back to our general data tab, remember we're using these serviceability load combinations for this design. We will consider crack control according to 1061. We also can turn on our deflection checks. Now you'll notice I have a new table here called deflection data. When I turn this on, we can activate long-term deflection according to 9825, where you can input the duration of the load here, and this will apply additional factor to your immediate deflection. The increase the required longitudinal reinforcement automatically for SLS design is turned on, and then we also have the ability for minimum skin reinforcement according to 10.6.2, which is turned off by default. The final table here is deflection data. So because we're checking deflections now, you'll notice that we have all of our members listed here, members 1 through 11. We have the length of the members set at 16 feet. If we wanted to put in a pre-camber, we could also do so. Now, most importantly is the limiting deflection ratio. We can use this drop-down box to select any one of the values shown here. The default is L/240, or we can put in a user-defined as well. So now the limiting deflection for our columns will be 0.768 inches. Now, jumping back to the reinforcement group, this only covers my columns for my first floor. What else I can do is just to easily make a copy of the current reinforcement group. So now you'll notice I have columns listed twice here. So I can go to number 2 and I can rename this to ribs. I can graphically select the rib members I'd like to apply this. So we'll choose our 2 bottom members here, 30 and 33. I click OK. And now I can just simply modify any of these settings that I would like that are specific to my rib design. So for example, I want to consider only 25 M's for my longitudinal reinforcement. The stirrups, we can leave the same. The reinforcement layout, of course, it's not ideal to place a reinforcement uniformly surrounding with this member. So instead, let's change it to symmetrical distribution. We also have the ability to distribute the reinforcement over the complete slab width. So this is our effective width. We can distribute that reinforcement to the top there. Other than that, again, we'll keep all of these settings the same. Under the deflection data, we now have members 30 and 31 listed here with a limiting deflection ratio of L/240. So our max deflection for these horizontal members are 0.768 inches. So we're finally ready to run our calculation. Now you'll notice that this will solve rather quickly because we already have all of the internal forces from the calculation from all the different load combinations. We're just bringing them into this add-on module. We're applying the CSA equations and determining the minimum reinforcement from the analysis to come up with our results. The results table are available to us. We can view the required reinforcement by member. For example, if I pull this down, you'll notice again that the table is synced up in the background with exactly which member I'm looking at. We have required reinforcement for the longitudinal bars as well as the shear reinforcement. So this is based only on the analysis and taking into consideration minimums, of course, from the standard, but probably what we're most interested in is the provided reinforcement. So you can see here that the program has come up with the correct reinforcement to use to meet those required reinforcements. And we have this shown, first of all, for our longitudinal reinforcement for all of our columns. We also have our rib elements shown here, so we can kind of rotate this picture around to see those T-beams and exactly how the longitudinal reinforcement was determined. Shear reinforcement, same concept. We can view all of our columns, but we're just currently viewing how the stirrups were defined as well as the spacing. Now for any one of these pictures, what's nice is I can double click in the white space and it brings me up to a larger picture here of the reinforcement that I can rotate. I can add this to my printout report. But let's say, for example, I'd like to make some modifications to this provided reinforcement. And I'm looking at my 1710Ms that are defined here, and they're spaced at every 1 foot. But I'd like to decrease that spacing to maybe 10 inches. What I can do then is just to modify this spacing to 0.82 feet. I click OK. And now you'll notice that the program automatically updates the number of reinforcement stirrups that I'll need. So I can exit out of this table here. I try and click in another table and the program gives me a quick warning saying, hey, you've changed the provided reinforcement. Let us recalculate just to make sure that you're meeting the required reinforcement. So we click recalculate. The program just thinks pretty quickly and then we'll determine if the changes are allowed or not. The serviceability checks are also shown here for each one of these members. This would include our deflection checks, but it also includes our cracking checks. So we have a minimum reinforcement that we must meet according to 10.6.1 for our serviceability design. So the program will come up with a design ratio for all of our members shown here for those two checks. Now, all of this information is shown within these tables, but we can also view it graphically. So what I'd like to do here under my results is let's take a look at maybe this same column line that we've been working with, but only the first level. I'll create a visibility by the selected objects, and what we can do here is to turn on the required longitudinal reinforcement. So again, this is from the analysis. We can see our diagram shown here. We can overlay on top of this the provided reinforcement. So remember, this is the rebar that the program has come up at the applicable spacing, and we see that overlaid in blue right on top of the required. Now, in all cases, the provided reinforcement should be greater than the required reinforcement. In our case, it is today. So we can view all these different results graphically here in terms of these diagrams. We also can display a rendering of the reinforcement as well, which is just nice to see how exactly this ties in to the rest of the structure. If I cancel my visibility mode, everything that I just showed you for the columns is also available for our rib members. So we can see the reinforcement displayed here for our T-beam. Again, with those effective widths considered. So that is a general overview of our member design. The next thing that we would like to jump to, of course, is our surface design. And under the Data tab, I can access RF concrete surfaces by double-clicking on it. And again, what this is going to do is to bring up a simple dialog box that looks very similar to what we're using for RF concrete members. We can choose the CSA standard from our drop-down box, and just like what we did with our members, we'll choose our strength load combinations, move them over to the right-hand side. Serviceability load combinations, we'll select those and move these over to the right-hand side. Now, under the serviceability limit state, we have a couple options here, analytical and nonlinear. Nonlinear, of course, would be RF concrete nonlinear, that module extension I mentioned. But under the analytical settings, let's take a look at the detail settings here. For the serviceability, and in particular for our surfaces, we can consider crack control, once again, according to 10.6.1. We also can turn on the deflection check. So this is what is required, or you do need RF concrete deflect, which is that add-on module extension to run the deflection checks within this add-on module. When we turn that on, the program just gives us a quick warning saying that the determination of the required longitudinal reinforcement for the serviceability limit state design does not include deformation checks. So just so that you're aware of that. We also can activate long-term deflection according to section 9.8.2.5 with the duration of our load set here. So again, RF concrete deflect is that add-on module extension that's necessary. So once again, just moving down our list, we have our material properties available to us for both strength. We would select the reinforcing steel properties from our drop-down box. The surfaces table is listing every surface available within the model, and as well as the thickness here. The deformation analysis, again, because we turn on RF concrete deflect, we have all of this information available to us. We need to define what is the limiting deflection ratio for these surfaces. Is it based on the minimum boundary line over 250, the maximum boundary line over 250? And if we have any question about what does this mean, minimum versus maximum boundary lines, you can click this little info button down here at the bottom, and this will tell you exactly what the program's referring to. Now in turn, you can just select a value here and enter it in manually. Let's say I don't want to see any higher deflections than 1.5 inches. Now currently this is being input for all surfaces with this all checkbox here. If you want to individually select the deformation limiting deflection ratios for different surfaces, you can do them by groups here by selecting those graphically. Is the deformation related to the absolute or relative system? So with this information, we can click this info button again. This gives a nice picture of what we mean by, do we want to compare this to the undeformed system or the displaced system here? Again, absolute versus relative deflections. And finally, we have our reinforcement tables here, again, where a majority of this work is done. So we can give this first reinforcement group, we'll call it floor 1. The surfaces will not be all, but rather what I'd like to do here is to only graphically select surface number 1. And I click OK. So you can see surface 1 is populated. The reinforcement ratios. So for example, this first one, the minimum secondary reinforcement is set by default at 20%. This will take 20% of the controlling reinforcement direction, direction 1, and will apply this 20% in the secondary direction, direction 2. Now this is of course unless direction 2 requires additional reinforcement from the analysis, but this is at a minimum what we'll place in that second direction. The rest of the options here, these really just compare the area of steel to our concrete cross-sectional area. The reinforcement layout. Here we have the ability to specify either a clear cover or just a cover. So whether it's related to the centroid of the reinforcement or the edge. Now in our case, we'll choose the centroid of the reinforcement, and I want to define my initial cover at 1.0 inches in both the top and the bottom and in both directions. We can rotate the reinforcement as well. So currently this is related to the local x-axis, but if you need to rotate that at a particular angle, you can enter in that information here. The longitudinal reinforcement. The first option is to give the program the provided basic reinforcement. So what I can do here is to use these detail settings where I tell the program, okay, I want to consider 20 m's at 8 inches on center. So all I need to do here is to type in the diameter, which is 0.77 inches at 8 inches. You'll notice the reinforcement area is automatically calculated for me. I'm going to apply this to the top and bottom reinforcement and in both directions. So when I click OK, that 0.7 inches is now my reinforcement area that I'm going to start with. Now the second option is the additional reinforcement. What do we want to use for the serviceability limit state design? And you'll notice that we have 3 different options here, which I believe are best explained again with this little info button to give us a nice graphical representation of what's going on with these 3 different selections. The provided basic reinforcement is shown with this smaller rectangle here at the top. Then the program might inevitably come up with additional required reinforcement. So the program's just asking us, based on this green line here, what do we want to use for the SLS design? So we're going to use this second option here where we'll take the peak of the required reinforcement and we'll apply this for the SLS design. But again, refer to this info button here to get a better feel of what these different options are. So we choose additional reinforcement layout. Now we want to give the program a diameter here for any required additional reinforcement. We'll stick with those 20 m's. The longitudinal reinforcement for the check of shear. The program is pretty self-explanatory with this. It's either apply the required longitudinal reinforcement for shear resistance. We can apply the greater value of either the required or the provided reinforcement, or we can automatically increase the longitudinal reinforcement to avoid shear altogether. So we'll stick with this second option for today. Again, the CSA tab is specific to this standard, and a lot of this information is similar to what we saw in RF concrete members, so I don't need to go into everything with detail. But the minimum reinforcement here, you'll notice that we have minimum longitudinal reinforcement for plates according to 781. So this would be beneficial for our slab elements. The second option is the minimum longitudinal reinforcement for walls according to Chapter 14. So within the same add-on module, if we're designing our walls with a different reinforcement group, then maybe we'd want to turn off the plates, activate the walls, and now those minimums will be considered. The minimum shear reinforcement refers to section 11281, which is turned on by default. And again, the rest of these settings are the same. I will turn off the exterior exposure for my slab. And finally, we have the design method. So this is pretty theoretical, and I would refer you to the RF Concrete Surfaces help manual for a better explanation on what these two different options are. But by default, this is turned on to optimize the design internal forces. This is recommended for elements loaded by bending or tension. In the case of our slab, we have that today. The no optimization of design internal forces, this is recommended for parts mostly loaded by pressure. So this might be a wall element that's in pure compression, for example. And just like that, we are finally ready to run our analysis. So we can click calculation. Now this does take not too long, but again, for the sake of time, what I'm going to do is to jump to an already saved model where I quickly solved for the reinforcement design. I'm going to launch RF Concrete Surfaces here, which should pull up my saved results. And we now have our results available to us within table format. So I'm going to jump to the required reinforcement. And we immediately notice that we have quite a bit of red here telling us that the area is not designable. And this is never a good thing if we're seeing red. So when I jump down to the required reinforcement by point, though, I notice that there are quite a few points within the program. Again, I can see this kind of synced up in the background that we are getting reinforcement design. So what could be the problem here? And for this, I'm going to jump to the graphics view. And I'm still within this RF Concrete Surfaces add-on module, just viewing the results graphically again back in RFEM. And maybe I want to take a look at my shear reinforcement. This is the required shear reinforcement shown graphically, which I can select within my project navigator. And when I zoom in here and I look at my color panel, most of the slab doesn't require any shear at all. But obviously we're seeing these areas where these columns are framing into the surface where we have extremely high values of shear required. And these empty FE mesh elements means that this is not even designable. It's too high. So this is what we could definitely determine as a singularity issue. Now, when we're looking at singularities, we take a look at these columns. Sure, when we look at the rendered view, remember these columns are 14 inches by 14 inches, and they're framing into this 2D surface here. But what's happening in the background with any FEA analysis is that members are actually just represented by this single center line. So then we have these forces framing into this 2D slab at this single FE mesh point, and it's causing extremely high forces, and we don't have any load distribution. So what I'd like to do is to show you maybe some options here of how we can deal with singularities. Now the first option within this column framing into the slab is we can create something that's called a rigid zone. So what we'll do here is to model a rigid plate that will actually just be used to distribute the load from the column to the surface. It's about 14 by 14 inches, so we can account for the true dimensions of that column for the load distribution. For this, I'm going to turn on my grid, and I'm going to snap to this work plane here at this first column. We can draw a new surface up here in my toolbar with a rectangle via center. The stiffness type I'm going to select is rigid. So notice all my materials, my thicknesses are grayed out. This is because we're given it extremely high stiffness, and rigid elements are used for load distribution. I click OK. I snap to where this column is meeting the slab, and what I'd like to do here is to essentially draw about a 14 by 14 inch rectangular section. So I clear my results, and the program immediately gives me a warning saying the new surface lies directly upon another surface. Do we want to integrate them? Yes, we do. So what you'll notice here, if I turn off my grid and maybe we turn this back to a wireframe view, I have my slab, but the program has placed an opening within that slab, and within the opening I now have this rigid plate element for better load distribution. We could even take this a step further if we wanted to add some type of drop panel. Well, again, I would just go here to a new rectangular surface via center. I would change the stiffness type to standard. And remember, our slab is currently 10 inches thick, so maybe we'd like to create something more that's 14 inches thick to deal with those higher shear areas. I can click OK. I snap to this center point here, and then I could draw in my drop panel. Again, we get the warning saying that the new surface lies directly on another surface. That's okay. So I have my original slab surface here. That's 10 inches. But I have my new surface, which is the 14 inches thick. And then finally, I have my rigid zone here indicated by this rigid plate. So this will certainly alleviate a lot of those singularity issues. Now, in turn, I also want to show you how we can use what's called average regions to kind of smooth out these high stress points. So I'm going to select everything that I just generated, and except for that center point there, I hit delete. What I'm going to do now is to apply what's called an FE mesh refinement. So every area where these columns are meeting these slab elements, I'm going to hold down my control key to select these various nodes, and we're going to do so here within our third column line, and finally we have one more column out here. I can right click on one of these nodes and I can apply a new FE mesh refinement, which is exactly as it sounds. We're going to create a new definition type here where we set the radius at 3 feet. The target inner length will be 0.1 feet, but we're going to transition back to our 1 foot global settings here. I click OK through all these dialog boxes. I now have an FE mesh refinement symbol. I can go to calculate, generate FE mesh. The program will now create a much smaller FE mesh around these particular areas and transition back to the 1 foot setting. Now, this is not going to take care of our singularity issue. All that we're doing here is isolating it to a much smaller FE mesh element rather than the 1 foot settings that we had previously. So that's the first step. The second step is we can go to our project navigator and we can right click to create a new average region. So within this dialog box, what I'll do is to graphically select surface number 1. I click OK. And the average region is also exactly as it sounds. We're going to average out these forces over a particular region on surface number 1. We're going to average out the forces in all 4 directions, so I'm going to check all 4 of these check boxes here. It will be a rectangular region with the dimensions of 2 feet by 2 feet. Now, a common question is, well, how big should I make my average region? And this really is up to the engineer's discretion and your particular model. You don't want to set this to something too large where we're averaging out forces and not really taking into consideration what the true internal forces and stresses may be at that location. Then we want to choose also the center of the average region, which I'll just click on that first column here. My points are populated. So I click OK, and we can see the average region symbol shown to me here. I can select this, hold down my control key, and once again utilize that drag and drop feature just to make quick copies here of the average region along each of the columns. Now I even have the ability to select multiple average regions. I can hold down my control key and I can drag and drop to the second column line. I can do the same thing here, and let me select these again. We're going to select our 3 average regions at the second column line. I hold down my control key and we're going to, sorry, I keep selecting this node. Hold down my center wheel and we're going to, there we go, make another copy, and you can see I accidentally dragged something. Let's undo that. Let's try this again. We'll just do each one individually, no problem. Using this drag and drop feature, making a quick copy of the second column line, and finally we have our last one here. We can delete this unneeded one up at the top. Okay, so that's how we can make quick copies of those average regions. You can even select this entire floor and copy it up to the second floor as well. Now, it's not as easy just to launch RF concrete surfaces here and to rerun the calculation, what we'll actually find is that we're still getting those non-designable regions. And the reason why is because under the Details tab, I need to apply the average internal forces for both the ULS and SLS design. So without this checkbox turned on, those average regions are ignored. So we would want to rerun the calculation, and once again, for the sake of time, I've already done so with an already saved model here. And with those average regions taken into consideration, like I just showed you, we can launch the RF Concrete Surfaces add-on module to view our results. Now, with the addition of those average regions, we're now seeing relatively good results within this table. We have our required reinforcement with this first column. We have the basic reinforcement. Remember, these were the 20 M's at 8 inches on center given to us in the second column. So then the program will tell us, okay, then this is the additional reinforcement that is needed within this surface. Serviceability design, you are going to see here, and it looks like we have some checks that need to be redone for our cracking. But the program will let you know here if you are passing the deflections, which we are. And then when it comes to our cracking checks from 10.6.1, you'll also get, if we're not passing those, you'll see this red sad face here, obviously. And then we'll want to adjust maybe the diameter and the spacing of our reinforcement to make sure that we're passing there. Okay, so once we are done viewing this information, we can also view it, of course, graphically, like we've already seen. What might be beneficial is to view the required reinforcement here based on the analysis for the top reinforcement in direction 1. We can view the top reinforcement in direction 2, as well as bottom reinforcement. Of course, we'd expect more bottom reinforcement for higher bending moments spanning between the columns. Shear reinforcement is given. You can see what a significant difference that those average regions make. We still have some required shear reinforcement even outside of those average regions, but that's probably to be expected where we have the columns framing into the slab. So that was a quick overview again of the RF Concrete Surfaces design. The last thing that I just want to show you is that we currently have let the program kind of optimize where we're putting all of this reinforcement. Under the Details option, you do have the ability under Reinforcement to manually define the reinforcement areas as well. So what I mean by this is when we click OK, you'll notice under Floor 1, and we take a look at the longitudinal reinforcement, this looks significantly different. We still have our provided reinforcement, but if we would like to select some rectangular regions where we'd like to add some additional reinforcement, we can kind of control that ourselves. So for example, we choose rectangular reinforcement. And let's say, for example, I'd like to add in 0.77 inches, again, those 20M rebars, and the spacing will be, let's say, 6 inches. So we only want to apply this to the top region, and we'll apply this in region number 1. Then we can graphically select here where we would like to put this. So, maybe we choose this region up here. We can select a rectangular area. We click OK. We do the exact same setting here, but this time the program remembers all my settings. I'm going to change this to direction 2, and I click OK. So now within this table format, what we'll be able to see is that additional reinforcement at the top. I can view this graphically by taking a look here within my model, and you'll notice that my provided reinforcement is all set in blue. Now the additional reinforcement is set in red here, applied to those relevant FE mesh elements. Now I can highlight these 2 additional reinforcements at the top, and we even can use the Move Copy tool here. So I can specify that I'd like to move and copy this reinforcement to my second column, and I click OK. So now I can view this information by clicking again. Well, now it's shown in our table here. We have all 4 additional reinforcements shown. I can go back to my graphical view And we can kind of zoom out here to see that additional reinforcement applied to the top of the columns. Now maybe we'd want to do the same scenario for higher bending forces along the bottom of the slab here for a rectangular area spanning between the columns. So again, just a little bit more control over where you're replacing that additional reinforcement rather than having the program determine that for you. So that's just something real quick that I wanted to show you, but of course we don't have time to expand on that much further today. So we'll go ahead and conclude our webinar today. You can find more information about RFEM and these concrete design add-on modules on our website at dlubal.com. We also have our web shop where we're pretty transparent about all the pricing information as well. I always encourage everyone to follow us on our social media channels. For example, YouTube will have videos and recorded webinars such as this one available to you. We also try and announce on these various social media sites just events that are coming up, such as online training, new technical articles, and FAQs. If you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office at info-us@dlubal.com, and the phone number is 267-702-2815. We do have a couple of online trainings coming up. So these are really geared towards new users within RFEM to show you the basic functions. This will be next week on May 20th, as well as one scheduled on June 25th. The cost is $250. It's a 4-hour training available for PDH, and you can register on our website at dlubal.com under support and learning, and you'll find online trainings. We will have more upcoming webinars as well. Again, you can register for those on our website as they come up, but most of you typically register through the reminder emails that I'll send out a week or so before the webinar will take place, so keep an eye out for that. PDH certificates will automatically be emailed to all participants today who were here for the full presentation. That is required from the states which we are pre-approved providers that participants are here for the duration of the full webinar. So those will again be automatically emailed out to you. Now, if you yourself did not register with your own name and your own email and you're wanting PDH, you will need to request that at our email address shown here, info-us@dlubal.com. So again, if you watch under a colleague's registration information, for example, please request the PDH through our email. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at the next webinar. Thank you.